Okay, all right, let's start. So, last lecture, this is where we were. We were looking at noise margins. And so, this is a summary of what we had discussed. We had said that in order to define noise margin, we need to define the logic 1 and logic 0. And so, if we select a voltage from VOH to VDD, any voltage greater than VOH is considered as logic 1. Then we can correspondingly define a voltage VIL. This is the maximum voltage that I can apply so that I get a valid 1. And similarly, if I define a V0L, from 0 to VOL is the logic 0, then I can define a maximum input voltage that I can apply in order to get a valid logic 0 here. So these four voltage levels we need to define: VOH, VOL, VIL, and VIH. And the noise margins then are the difference between VIL minus VOL is the noise margin for the logic low level here, and VOH minus VIH is the noise margin for the when you apply a high voltage, a logic 1 at the input here. And the issue then is, so these are the definitions. The issue then is, how do we find this VOH, VIH, VIL, VOL? How do we find these things? And as I was suggesting, that one way in which you could do that is you have a normal voltage transfer characteristics, V out versus V in, which is this black curve here. And then you plot another one where you flip the axis. This becomes voltage. This becomes output voltage. This becomes input voltage here. So you redraw the same voltage transfer characteristics, but with a different axis now. And in that, the largest square that you can fit in, that defines your under the constraint that NMH is NML. Then what you try to do is find the largest square that can fit into this particular one. And once you identify that, then your levels VOH, VIH, VOL, VIL, they all get defined, and you get noise margin lower side and noise margin on the higher side here. So once you define it like this, this is the most general way of finding the noise margins here through a plot like this. But this is not easy to do that by graphically plotting it out, finding the maximum square that can be fitted in. So the other way of doing that is you take your VTC, find the points where the slope is -1. So you get two of those. These define VOH and VIL, and these define VIH and VOL, and use these to find the noise margins here. So you use unity gain points here. Now, what I'm saying is that this is the most general one, and then you can use this, but we'll just see an example. I can always construct a VTC where you may not have a slope of -1, or the slope of -1 may be not a single point, but maybe a larger region. Whether those VTCs can actually be constructed or not, that's a different matter. But I can always draw a graph on which there is no unique -1 point, -1 slope point here. And therefore, these definitions in that sense will fail. So the most general one is here. The most general method is, according to this, all that you try to do is fit this particular square here. But as I said, it's not convenient, and we try and use this particular technique to define our noise margins low and high. And but here is there's one more twist that I was talking about. So here, when you take a slope of -1 and -1 here, you get VOH, VIL, VIH, VOL. Fine, and you define noise margins. But many textbooks won't do that. Many textbooks would use an alternative definition. What they would do, this is what I was pointing out, that yes, you have drawn a slope and you get this, but they will define noise margin in this case as VIL -0. You know, if your VTC goes from VDD to 0, we'll come in a minute. What happens if the VTC doesn't start from VDD and doesn't go to 0? Okay, that's a separate case. But suppose it starts from VDD and does go to 0 output here, then NML is VIL -0. And NMH is VDD minus VH. They ignore this particular point here, VOH and VOL. They just define NML and NMH in this particular manner here. So I guess, as I was telling, the idea is that normally your device it doesn't have any noise, so 0 VDD, 0 here. If you add a noise equal to NML here, this gets to VIL, and then this goes to VOH, and the system recovers and works fine. All right, so there's no rigorous justification for defining it like this. You can check if you use this concept of noise margin, and if I start putting noise at every input, the system would fail. The system would fail in this case. But this is a very common definition also. In fact, many of the textbooks would define it like this. So NML is VIL minus 0 and NMH is VDD minus VIH. That's the definition that they would use. They'll ignore this particular point here. What is this VOH and VOL? They'll ignore that. They'll just take VDD minus VIH and VIL minus 0 here. All right. Okay. Now, what happens, as I said, in case this was starting from VDD and going to ground, what happens if it doesn't? VDD somewhere here and the characteristics doesn't go to ground. In that case, we need a little bit modification, because remember what the justification of this is, that normally when you don't have any noise, there's a stable value of input, output, and all that is going, right? And the stable values in this case were 0 and VDD. And then how much noise can you add? And still the system sort of recovers back and gives the proper values. System gives proper values. The amount of noise that you add still gives a valid logic high and logic low level here. So this is okay when this is 0 in VDD. But in the next case, I don't have 0 in VDD here. So for example, even if my VDD is 3.3, if I apply 3.3 here, note in this case, if I apply an input of 3.3, the output is not going to be 0. And if the output is not going to be 0, then the next output here is also not going to be 3.3. So VDD and 0 are not the stable values in this case. That in the absence of noise, if I take a long chain of inverters, it's not that everywhere I get VDD 0, VDD 0, VDD 0. I don't get that. In fact, I'll get something else. The stable values would be some VOH. Now, please keep in mind, this VOH is something else. Don't confuse it. I've deliberately written in small VOH. It would be some high value, some low value, some high value, some low value, right? A consistent set of values. That if in a long chain of inverters, if I start and put a VDD here, it will take some time for the values to stabilize, and eventually it will stabilize to some VOH, VOL, VOH, VOL. What are those stable values? How do we find that out? Well, one way of doing that is a similar plot that we have been doing. You take this as V out and take this as V in, same characteristics, you replot it. And the stable values that you see here are points like this here. This will define your VOH and VOL. Okay, so if in a long chain, then you will have, the system would stabilize at these points here. Okay, think about that. And then the noise margin then will be defined as, because the stable values are VOL, so instead of VIL minus 0, we define it as VIL minus the small V0L. And similarly, noise margin for the high side would be the VOH, the stable value that is there, minus VIH. VIH and VIL are still defined as minus 1. They're still defined as these values here. This is still VIL and this is still VIH, except that we don't call this VOH here, this point, and we don't call this VOL. These are defined from here. Okay, and as I said, in many cases, these points would actually go here, would merge with the axis here with VDD, so it would turn out to be 0 here, turn out to be VDD here. So then we go back to the earlier definition. In terms of noise margin, the most general description of noise margin is here. This is the definition of the logic 1 and logic 0 and the largest square that you can fit in. That's the most general one. This one is trying to do that. As I said, in some cases works, and I can always construct a VTC where it may not work. But this will always work for you. Always work for you, and is the most general one. And after that, so that's what I'm pointing out, that when you read books, you'll see confusion. You'll see somebody defining it like this, and VOH, they will say VOH is here, and VIL is here. So they'll take a difference of VOH and, use this one. And somewhere else, they will use, let's go back here, they'll define it like this. So you may still see VOL, right? And you may still see VOH, but it's not this VOH. It is this stable value, something else VOH. It's not at minus 1 point, at slope of minus 1. So there is a confusion in the books. Different books seem to be, the modern textbooks would all use this. Some of the modern textbooks will all define it, the minus 1 slope here, and they will define it as VIL minus V0L and VIH and this. They will use this. Okay, so here is an example of VTC. Hypothetical VTC, slope 0, slope greater than 1. Right? Where is slope equal to 1? Well, what we can say is I can construct a infinitesimally small region here where the slope goes from 0 to some higher value, and that point would be, I can even take this as -1. There is no unique place. So I'll define this as, well, -1 slope will also lie at this point because slope is 0 here and slope goes to something higher here. So -1 slope would be somewhere in between. And what is that in between? The same point here. So I could do that. I could say this is my -1 slope point. And so VOH is equal to VDD and VIL equal to this point here, V1. And then I draw another slope here. Well, this is slope of -1, I'll say. And here is VOL equal to 0 and VIH equal to VDD minus V1. And then we'll get our NML equal to V1. So NML is equal to VIL minus V0L. V0L is 0. VIL is V1. So we'll get this threshold value as the noise margin. Right? But you can see there is no -1 slope here. And as I said, I can take this and I can construct another one where it's 0 and then there is a region of -1 slope. A big region of -1 slope. And then something else. So -1 slope point is not a point. It's a region. So what is your VIL then? The definition will fail. What is VIL? Right? But the other one will not fail. The other one is, as I will show you, once you draw a plot and you draw the other one and you find the biggest square that can fit in, that will never fail. That will always be valid. Okay, so that's the most general one. Anyway, this has something interesting in it. So we find, so given a VTC, as I said, we'll try and find the slopes, -1 point here, and we get VOH, VOL, and all that we get, and we define noise margin here. Now, note what I also want to point out through this example is that this is a gain 0 point, gain 0 region here, and this is a region where I have gain, and I have a fixed gain here, and I can define the gain. As you can see here, the y-axis changes from VDD to 0, so VDD to 0, and x-axis changes from VDD minus V1 minus V1 here. So this is the gain of this region here, and maximum gain that I can get from my inverter here, Gmax. And I can rewrite this as, note that NMH, I can take this one and write it as V1 by VDD equal to 0.5, 1 minus 1 over Gmax. And I can rearrange and write it in this form here. NMH by 0.5 VDD equal to 1 minus 1 over Gmax. Why am I writing like this? Well, realize that the maximum noise margin that you can get is 0.5 VDD. Half of VDD here. So NMH by 0.5 VDD is sort of a measure of how close do I get to the maximum. And what does it depend on? 1 minus 1 over Gmax. How large a gain can your inverter give? So many places where you would read, I mean, not necessarily in CMOS inverter, but in CMOS also, but many places you would see people, measuring the VTC and then taking the slope of the VTC and writing in the papers and books and all that, what is the maximum gain that I can get from an inverter? The maximum gain that I can get from an inverter. Now, why are they talking about maximum gain? How is the gain figure coming into picture? So this example is illustrating that. Why are they talking about maximum gain? The higher the gain that is there in my system, the closer my noise margin gets to the maximum possible noise margin that I can get, 0.5 dB. If I have a low gain system, note that if it's a low gain system, it will go further here. The V1 and all that will change and noise margin will decrease. Right? So a inverter which gives you high gain may in general have a good noise margin. An inverter with a low gain will give you low noise margin. That's a general statement. Of course, exceptions and all that you can find here. And so this simple example is illustrating that. The relationship between noise margin and the gain. The gain of my inverter that you see here. So gain is important, and you are generally looking for a large gain from your system. And as I said, that's why you have to use a transistor in order to make a inverter. All right, as I said, if I want to do the same thing using the most general method, so this is my VTC, normal VTC with V out here and V in here. Now what I'll do is I'll make this axis V out, this axis V in, and redraw the same curve. So this red one is the axis which is redrawn. And then I try to find the maximum square, which is this region here. Right? I don't require any -1 slope or anything. All that I have to do is Just redraw another characteristics, V out versus V in here, and try to fit the maximum square. And from this also we get an answer which is equal to 1. The noise margin, the maximum square that I can fit in, you can see here is 1 here and 1 here. So which is the same answer that we get from even this. If V1 is 1 volt, then the same answer we get. Okay, in this case. But as I said, this is a general method that you can use to find noise margin here. All right. So with that, let's discuss the inverter in a little bit more detail here. Our first inverter, simplest inverter that we can form. So all that discussion was related to how do we define noise margin. Okay. So these are the things that we are looking for from not just from an inverter, but from a digital gate. Any gate, NAND gate, NOR gate, whatever you are looking for, you are looking for these things here. Area, how much area does it occupy? How much delay does it have? How much power does it consume? And how robust is your design in the presence of noise, measured in terms of noise margin here. So an inverter like this has characteristics here. So if I want to measure the noise margin, what I will have to do is, remember, I'll have to figure out what is VOH, VIH, VIL, all those things I have to find that out here. Okay, VOH, we can clearly see, note that you can see that if Vin is 0, the transistor is off, output is VDD. So output remains VDD till you reach threshold voltage, close to threshold voltage. Then it begins to fall, and then eventually the transistor goes into linear region and there's some small voltage. So VOH is VDD here. VOH is VDD and VOL is some value here which is greater than 0 here. All right. Now, which definitions am I using for VOH and VOL? I'm using the last definition, the most common one, not the most accurate one. Okay, the most popular one. So VOH is VDD. Stable values for this inverter would be VDD and whatever is the value of VOL. How do I find? So VOH is very easy. VDD. How do I find VOL? Well, VOL, remember when you apply, let's look at this point here. When you apply VDD here, and what happens is that when you apply VDD here, the transistor goes into linear region. The transistor goes into linear region. The voltage here is small. Note that if you apply VDD here, VDD let's say is 3.3, threshold voltage is 1. So saturation would require that this voltage be 2.3. And this voltage is very small. Right? So we want it to be very small, and therefore the transistor is in linear region. And in linear region, what I did was I approximated so the current that flows is here will be VDD minus V out by RD. And since V out is very small, we approximated it as by VDD by RD, current. So we are doing an approximate calculation. So that's the current that is coming here. And the current that the transistor carries is beta VDD minus VTHN V0L. V0L is the drop here. I ignored again the quadratic term. VDD square by 2 is also there, but that's again very small. So we take this equation, we solve it, and we get, for these values, KPN, VTHN, VDD 3.3, we get a value of, if I assume W by L is 4 lambda by 2 lambda, RD 72K, we get VOL equal to 0.1 volt. So that's how we find. We equate the current that comes from here equal to the current here, use the expressions, and make some assumptions. Note that I ignored when I calculated current, I didn't write VDD minus V0L. Well, V0L is 0.1. There is a little bit of error. The current that comes in would be 3.2 by RD. I took it 3.3. Doesn't matter. I mean, first order calculation, these are okay. So V0L is 0.1. So it doesn't go to 0. The output doesn't go to 0. It will always stay above 0 here, 0.1 for 72K. Now, how do I choose 72K? We'll come to that later on. Why did I choose 72K? Is that the most optimum value? W by L, 4 lambda by 2 lambda makes sense. 2 lambda is the minimum length that I can use. 4 lambda is the minimum width that I can use according to some rules. So I've used the minimum size transistor. I want to keep the area minimum, and therefore I used a minimum size transistor, 4 lambda by 2 lambda. So that makes sense, that there is some justification for why one took 4 lambda by 2 lambda from the area part. Why one took RD equal to 72K? Well, right now is arbitrary. But remember, one of the things that you want, whatever resistor you use, you want this value to be close to 0. You don't want this value to be high. Okay? So 72K is not bad, is giving us 0.1, reasonably low value. If you want to use even higher, 90K or 100K, it will come further down. But remember, what is the price that you'll have to pay? we saw in yesterday's lecture how large this resistor was. So as you increase the value of the resistor, well, you can bring the V0L down, but the resistor occupies more and more area. So you can see that the price that you'll have to pay is the area part. All right. So if you really want 50 millivolt or 10 millivolt here, well, you'll have to increase it even further, 72K. Right. All right. So this is there, V0L. The next thing is, what is VIL? To calculate the noise margin, I need VIL. And VIL, to find VIL, I have to find a place where the slope is -1. I have to find a slope of -1. And similarly, to find VIH, I have to find a place where the slope is -1 on this side. So two regions I have to find where the slope is -1. Okay. So the first one I'll leave the detailed calculation for you to do in the homework. So what I'm saying is, note that what is really happening is the region is zero gain because the transistor is off. Then the transistor turns on. Once the transistor turns on, which state is the transistor in? Just when the transistor turns on. We looked at that question earlier also. So you have applied the voltage a little bit larger than the threshold. The transistor is turning on, and the output is what? Still close to VDD. And note that the transistor is in saturation region. And in saturation region, gain is usually large. So what happens is, you go from gain equal to 0, and you start going to higher gain very rapidly because the transistor is in saturation region, right? So one very simple approximation could be VIL is simply equal to threshold voltage. I don't even find the -1 point in this case. I'm not saying for every case. In this case, VIL is very close to the threshold voltage. All right. If you want, as I said, I'll leave it for the homework. Find this point -1, and if you do that accurate calculation, it says VIL is 1.07. It doesn't happen at the threshold point. It happens a little afterwards, obviously, but it's 1.07. So we are not too bad by saying that the VIL occurs at the threshold point, 1 volt. So NML is, we found out VOL earlier. VIL is 1 volt. If you want accurate value 1.07, you can plug it here, you get 0.97. That's the noise margin on the lower side. NML is 0.97 here. Well, NML by 0.5 VDD, this is the max. Remember, maximum noise margin that you can ever get is 0.5 VDD. You can take a ratio here. This value is 0.59. All right. You'll never achieve the maximum value, but this is not bad. 0.6 times the maximum value here. So you're within 40% of the maximum value. Obviously, you should aim for higher, but okay. NML is here. VIH, I'm not showing here. VIH is, you have to find another point where the slope is -1. You have to find that point where slope is -1. If you do VIH, you find 1.7. And NMH then becomes VDD minus VIH is 1.6. So NMH is higher as compared to NML. Now, why is NMH higher as compared to NML? Note that this is 0.97 and this is 1.6. Is that a good thing to have? What did we say? If your both the logic levels are equally susceptible to noise, you should try to balance both of them, right? You should try to balance. So what we should try and do is, this is 1 volt, this is 1.6 volt. My effective noise margin is then only 1 volt, because it will be determined by the weaker or the lesser value here. So now the issue arises is, should I now do something to my characteristics and sort of decrease this value and increase this value, right? Shall we try and increase this value? Now, so what you are seeing is that there is asymmetry. This value is lower as compared to this value. There's asymmetry. And we said one of the ways in which you can measure asymmetry, well, one is the detailed shape and all that. You see the shape is also not symmetrical. One of the ways of measuring asymmetry is what we call as the inverter threshold voltage. Right? We said take a point, draw a line here and find out where it intersects inverter threshold voltage. And we said for symmetrical characteristics, inverter threshold voltage should be in the middle, VDD by 2. Right? So how do we find inverter threshold voltage for this? Remember, the definition is at the inverter threshold voltage, V out equal to V in, which effectively means that the transistor is in saturation region. right? So note that the V out equal to V in, so somewhere I'll have here. All right, so V out equal to V in here. Okay, so let's go back. So transistor is in saturation region, and because V out is V in, it's effectively like gate and drain shorted together. So it's in saturation. This is the expression for current in saturation. And this transistor current must be balanced by current in the resistor. So we have this equation here. And you need to solve this equation. You need to solve this quadratic equation. So a little bit messy, but you can solve it. For RD equal to 72K, V out equal to V in, we get inverter threshold voltage of 1.5. So what does this tell us? That the 1.5, the ideal value is 1.65. So what does it mean? That my characteristics is a little bit shifted towards the left, right? Shifted towards the left because it is 1.5. This point should have been 1.65. So if I take these characteristics and a little bit shift it to the right, I may get inverter threshold voltage of 1.65. Right? So now the issue is the following. How do I shift it right? So you're all saying that the inverter threshold voltage that we just calculate is 1.5. I need inverter threshold voltage of 1.65. And I need to shift the characteristics, my entire VTC that you see here, I need to shift it towards the right. Note that if this graph shifts towards the right, this intersection point will also shift towards the right. So that's the issue that we are talking about. Shift characteristics to the right to improve NML. So NML will improve, NMH will go down. That's what we are trying to do now. Okay, so we started off with the default design here. All right. Now, let's come back to this general question first. Note that this is our characteristics. Let's say, let me remove this resistor for a moment and say instead of a resistor, we'll call this as some pull-up device. Now see whether that sentence makes sense. Pull-up device. Why am I calling it pulling it up? Note that in an inverter, this node, this output node, has to be either 0 or VDD. Right? Either 0 or VDD. Suppose it is at VDD. How does it come down to 0? This device pulls it down to 0. When you turn this device on, it pulls this particular node to the ground. So we call this device as pull down device. And who pulls it up to VDD? It is the resistor here, which is connected to VDD. So we call this device as a pull up device. So in general, an inverter you can think of what? A pull up device and a pull down device. Right now we have put a transistor here and we put a resistor here. Well, you could think of something else. I could think of a resistor here as a pull down and a transistor as pull up. And I can think of a transistor as pull up and a transistor as pull down also. I have all these options available to me. Obviously, both cannot be a resistor. So I need a transistor there as a gain element, right? So think about this as a pull up and a pull down. Okay? Right now. So if it's a pull up and a pull down device, and let's say it has a VTC like this. Now note that pull up will have some resistance and pull down will have some resistance here. Now I want this VTC here to be shifted towards the right. Shifted towards the right. What do you have to do? Can you all see that I will have to decrease the pull up resistance? One way of shifting it towards the right. Whatever is the device, I have to reduce this resistance to shift it towards the right. This is an important point. Because note that what keeps it up to VDD? What keeps it up is the pull-up device keeps it up. And what brings it down is the pull-down device here. If I make the resistance smaller, it will remain high for a larger region here. If I make the resistor smaller, it will make it stay high for a longer region here. It will be like this here. Not exactly shape and all that may not remain the same. Keep in mind that what we are talking about is the shifting part. If I decrease the pull-up resistor, the characteristics would shift towards the right. Why? Because now this has become stronger. Lesser resistance means this node is more strongly connected to VDD here. More strongly connected means it will stay on for a longer fraction of the voltage here. And then it will come down. Similarly, if I decrease my pull-down resistance, I'm making this stronger. Resistance becoming less means this is becoming stronger. and which means this is more strongly connected to the ground here. So the characteristics will shift towards the left. So this is a general notion that you should keep in your mind. How do I shift things towards the right? How do I shift things towards the left here? Now, obviously, you could have also said the following. If I want to shift, let's say this is my original characteristics here. I want to shift it towards the right. And the only thing that I can change is pull down. What will you do? What will you do? I want to shift it here, so you increase the pull down resistance. So either you decrease the pull up resistance or you increase the pull down. Both of them are in some sense equivalent. So that's what you have to do here. Okay. So keep that in mind. How do you shift the characteristics to the right, or how do you shift the characteristics to the left? These are so think of this as a pull up element and a pull down element. Right? Okay. So now can you see that what will happen is, go back here. So I want to shift this characteristics towards the right. Can you see that I have two options? This is my pull up. What should I do to the pull up? Reduce the value of the resistance. So that's one way of doing it. Reduce RD. And what else can I do? Increase the resistance of this particular one. How do you increase the resistance of this particular one? You make its size smaller. Note that the current that flows is proportional to W by L. The current that is W by L. If you reduce W by L, you reduce current and you reduce the resistance. You increase the resistance. So two ways in which you can shift the characteristics towards the right: decrease RD and decrease W by L. And you can shift it. Now I can't decrease W by L. It's already minimum. 4 lambda by 2 lambda is already minimum. So that option is close to me. So the only thing that I'm left with is decrease RD. Right? So we can do that now. So I'm showing you what happens. Okay, so in this case, you can see here that my original characteristics was here, W by L equal to 2, R is fixed, and as I change the size here, 2, 4, 6, 8, you can see the characteristics shifting left.
So once we got the point where we move from cutoff to saturation, will always remain the same.
No, so this is a simplified one, right? All that it says, well, in general, it will shift towards the right. But remember, as you change things, the characteristics also get distorted. The shape doesn't remain the same. Yes, this point that you see here, it may not. This is a general. This point, as I said, is VT. Suppose, and VT will not shift. So we see a problem there. All right. So that's a general notion that one is saying is characteristics will shift. It's not a complete lateral shift. Some part may shift, some parts may not shift here. That's what we will notice. Okay, but that's a general discussion that you have to decrease the pull-up resistance to shift it here. You have to decrease the pull-down resistance to shift it towards the left. All right. So this is what you actually find. So when I, for example, when I increase W by L, what I'm doing is I'm reducing the pull-down resistance. So characteristics is shifting towards the left here, as expected, but note that some points are not shifting. Some points are shifting a lot. And some points are not shifting at all. That's the nature of the circuit here. In this case, this is the option that is available to us. I kept W by L fixed. And as I said, we have to, our resistance was 72K, and we said we should reduce the resistance in order to shift it right. So 72K to 52 to, 62, 52, 42, 32, you can see all the graphs here. So we are able to shift it towards the right here. But a point where VIL is located, that is not shifting. Because as what we said does, VIL is VT, very close to VT, that's not shifting. Okay. But so what happens? Suppose I do use 32K. So here are two designs. This is a design for 72K. Look at the values here for 72K. And this is a design for 32K. Did you gain anything by going towards 32K? In terms of noise margin. Note that I went to 32K. VIL was 1.07. VIL just increased to 1.16. Didn't change much. It is determined more by threshold voltage. It didn't change much. Well, the characteristics did shift right. So VIH was 1.7, VIH became 2. On this side, the characteristics is shifting, so it became 2. So NML hardly improved, and NMH actually decreased. So I didn't gain anything. No improvement in NML, and NMH actually decreased from 1.6 to 1.3. All right. Anyway, maybe this was done too much. It is 1.72. It didn't come to 1.65. But even if we had tuned the value to 1.65, you would have seen VIL doesn't improve. VIH will decrease. You won't get much improvement. You won't get much change. But there is one benefit that you do get by going to 32K. That I have a smaller value of resistor. And there's one benefit because note that if VIL remains the same, and even though VIH has NMH has decreased, still my noise margin is determined by the lower value. And so noise margin is the same for both the systems. And I've used a smaller value of resistor 32K. And therefore it's a smaller area. So that benefit comes. Noise margin remains the same with the smaller resistor. And therefore I have better. But there's another sacrifice that I've made is VOL. If you look at it, VOL is 0.22 and VOL is 0.1 here. So the lower logic level has gone up. VOH remains 3.3, VOL becomes 0.22. So think about why has it gone up. Simple answer. All right. So here is we showed this yesterday. Here is our design for 80K here. And we saw that it occupies a large area and we want to reduce the area. So can I use, instead of 80K, 10K? I will reduce the area. See, area of the resistor is 35 times higher than the area of the transistor. Well, let's reduce the by a factor of 8, the resistor here, 10K. Well, the whole area now becomes smaller by a factor of 8 or so, roughly. It's become smaller. What is the price do you think we'll have to pay? If I put RD equal to 10K, well, let me give you the values. Same, RD equal to 10K. V0L goes to 0.72. NML becomes 0.28. V0L, lower logic level, which was 0.1 earlier, went up to 0.72. So what are we seeing? We are seeing area, delay, power, noise margins. You will always see trade-offs among these 4 quantities. Well, I tried to reduce the area. At the noise margin, see what happened. 0.28, collapsed. Right? So, yes, RD equal to 10K, but this is the price that we have to pay. All right, so this is with noise margin. Let's go to the next important point, which is we've already have some sense of area. How much area? We've done some layout and all that. We have some sense of area. We now know about noise margin. Let's go towards delay. All right. So delay is what we define it as. We call it propagation delay. Okay. So look at the definitions first. The definition of propagation delay is as follows. Input is this line here. Input is this black line here, right? Input is here. And we are applying this input to the output here and to the inverter here. So in response to this input, so it's going from 0 to high and high to low. In response to this input, let's say the output goes like this here. Output, when it is 0, the output is high VDD, and then the input is switching, the output remains till perhaps the input reaches about the threshold voltage, then the transistor starts conducting and then starts falling. This is simplified view. It will not fall linearly like this and rise like this. So the definition of propagation delay is the point where you find out the point where input crosses 50%, 0.5 VDD. And you look at the point where the output crosses 0.5 VDD. And the difference between the two is what we call as the propagation delay. Because remember, 0.5 VDD is our threshold voltage. So we say, well, the input has really become 1 once you cross this. That's where the input is 0 here. The input has sort of become 1 when you cross this threshold. And the output has become 0 when it has crossed this threshold. So that's why the difference between these two thresholds is what we call as, note the word tau PHL. Aside from that, you can also define what is the total time it takes for my output to fall time. You know, fall time is usually from 10% to 90%. The total time it takes for my output to rise, 10% to 90%. So TR and tau R and tau F also you can define. But these are the more important delay values, tau PHL and tau PLH. These are the two values that I have to find. All right, so how do we do that? Let's get to our inverter. This is our inverter, and note that you're never going to use any inverter or any gate isolated by itself. You will always have inverter connected to something else. So as a load, we have considered another inverter connected to this one. So we are interested in propagation delay of this one right now. And the load of this one is another inverter. Same size, same everything for the sake of discussion. And let's look at the case where my input is making a transition from VDD to 0. And so what we are looking at is the output will go from 0 to high, low to high. So we are looking at this kind of this thing here. So input is going from high to low, and the output will go like this here. Output will go in this particular manner, right? So what we need to do is, so I've placed a abrupt input here. Note that with zero transition. So for a simplified case here. And so this is my 0.5 point here. So this is my propagation delay. This is what I need to find out. How much time does it take for the output to rise to the 50% point here? Okay, so this difference. Now, why is the output taking time to rise here? Well, why? Because note that the moment you go from VDD to 0, what happens to your transistor? Transistor switches off. The voltage, input voltage is 0. 0 volts is less than threshold. The transistor switches off. This node is initially at 0, and this node has to be pulled up to VDD here. And who pulls it up? The RD here. RD charges. And why is it taking time? Because I have a capacitance here. And this node has a capacitance. And this node has to be charged up to VDD. Capacitance has to be charged up, and it's charging up through RD. That's the reason for this delay here. And that's the reason why you've also seen I've drawn sort of exponential here. Because CT is being charged by RD here. Now, where is this capacitance coming from? Well, the capacitance is coming from the transistors. Each transistor, recall, has between gate and drain, between gate and source, between drain and body, and between source and body. These four capacitors are always there. Gate and body, I've ignored it, just to keep things simple here. So what is the net capacitance at this node? The net capacitance at this node will come due to M1, and it will come due to M2. So can we see this? Net capacitance due to M1 will be what? CGD1 plus CDB1. Note at this point, between the gate and the drain, there's a capacitance here, gate and drain, CGD1. And drain to body. Where is body? Body is connected to ground. Between drain and body, there's a capacitance here. That's due to M1. And due to M2, between this node, gate to source, and between this node and this node, gate to drain. So four capacitors are coming at this particular node here. Now to calculate the delay, I have to calculate all these capacitors that are there. I have to find out these values. Gate to drain, drain to body, gate to source, gate to drain. Each one of these capacitors will charge. And each one of these values have to be found out. Right? And how do we find it out? Well, we've given you the parameters here, CGSO and all that. All these technology parameters are there. Let's look at it. How do we find here? Now, before that, there's further complication. Each one of these capacitors, the value of the capacitor depends on the state of the transistor. We've said that in general, these capacitors are not constant. It depends on the state. So let's quickly look at this one here. So when I go from VDD to 0, initially, note that my device is, initially I've applied VDD. When I apply VDD initially, so my device is going from VDD to, what am I saying? Device is going from, yeah, okay. So initially it is VDD, output is V0L, and this is VDD here. So what is the initial state of the transistor? Before I switch, the input is VDD here, output is V0L close to 0, and this is VDD. What is the state? Linear. Transistors in linear, this is in cutoff. This is obvious, input is low, transistor is cut off. Linear, because the output is very, very small, and so transistor is in linear mode. Now note that once this is 0, what is the state here? This is cut off. And what is the state of this one? Well, if this is cut off, eventually this will go to linear. But how will it go to linear? It will go from VDD to 0L. It goes from cutoff to saturation to linear. That's how it goes. So this transistor, why am I interested in this? How does this go? Because the capacitance of this one matters to me. To calculate CT, I have to know the state of the transistor here. Now, this is where during switching, this immediately goes to cutoff. Once I go to 0, this goes to cutoff. Fine. But this transistor starts from cutoff, goes to saturation, and then goes to linear. And in cutoff, there is one capacitance value. In saturation, there's another capacitance value. In linear, there's another capacitance value. Capacitances are changing. The other problem is, note that drain to body capacitance here. Drain to body capacitance is a PN junction capacitance. And drain to body voltage is changing. So that capacitance is also changing here. Okay. So these are the 4 capacitors that we need to find out. Look at the drain to body capacitance is here. It's a PN junction capacitance. And drain to body capacitance depends on the bias here. Alright, so this is a complication here. So note that the transistor, so it goes from cutoff to saturation to linear. Right, so gate to drain capacitance is over most of the region simply equal to CGD0 times the width here of this first transistor, W1, because it's in cutoff. Gate to drain of the second one, it starts from cutoff, where it is CGD0 W2. In saturation region, it's also CGD0 W2. Once it goes to linear, well, the value changes. I have not written that. Drain to body 1, this is how you calculate drain to body capacitance. Here, there is an area part and there's a perimeter part. All these things are given to you. CJ, PB, everything is given to you. But you have to know the drain to body voltage in both cases. And drain to body voltage here is continuously changing. As this node is charging, the drain voltage is increasing. So this capacitance is changing. And so it's going from 0 to 0.5 VDD. Initially, drain to body is 0. And then it goes from 0.5 VDD here. So this capacitance changes here. And CGS1 of this one goes from cutoff to saturation, so it shows here. Alright, so let me just quickly show what the capacitance values are. So in order to compute the capacitances, even these values that are given, I need the area drain and the perimeter drain, everything else information I have. Alright, so we did a layout of this transistor. Area drain was 40, perimeter drain was 22, and we can determine the capacitance, the drain to body capacitance, assuming drain to body voltage is 0. So it turns out to be 5.7 femtofarad. Note that the perimeter part is 4 femtofarad, the area part is 1.7 femtofarad. How important is the perimeter? Perimeter of the drain. That gives you more as compared to the area here. The total capacitance comes out to be 8.5 femtofarad. Total comes out to be 8.5 femtofarad. Now out of that, how much is the drain to body? 5.7. Out of this 8.5, 5.7 is the drain to body. And that's the point that I'm trying to emphasize, that if you don't do the layout, then you don't know the area drain and perimeter drain. Then you don't know the drain to body capacitance. Right, so the layout information is important to extract the drain to body capacitance, and you can see here it's a very, very large fraction of the total capacitance. Now, once you know the total capacitance here, note that the transistor is off. It's a simple RC charging, and one can calculate the delay, which is 0.693 RD CT, which comes out to be 424 picosecond. So we have our tau P low to high delay of 424 picosecond. If I had not included drain to body, the delay would have been 137 picosecond. So as I said, most of the time when you do a simulation, the drain to body area and perimeter by default are 0. In almost all the simulators, by default, they are putting it 0. And W and all that, anyway, you are entering into the simulation. So when you do the simulation and you don't enter area and perimeter drain, you'll get 137 picosecond delay. And you may feel very happy that 137 picosecond is very good. But when you put area at perimeter, it comes out to be 424. There's so much difference between the two. Drain to body capacitance is extremely important in a MOSFET. All right, so let's stop here.